In the darkest quiet of space, a magnetar turns with a magnetic field so strong it can strain a crust like glass and light the void with sudden, silent power. This is not a story of noise. It is a slow journey through thresholds and release, through heat that creeps along hidden seams, through halos that fade like mist, and through the calm physics that holds even the most extreme stars in balance. If this kind of cosmic sleep science helps the night feel softer, tap, like subscribe and turn on notifications for more long-form space journeys like this. A magnetar appears calm from far away, yet its calm is a kind of pressure held in place. Magnetism stores that pressure as strain and strain can break a crust and release a sudden flare. At this distance, the object would be a steady point with a dry, restrained glow. Closer in, the point becomes a compact sphere with a sharp limb and a thin haze hugging the edge. Across the surface, darkness is cut by hairline seams. Those seams trace boundaries where the solid shell is most stressed. Near a pole, the light is slightly harder and more concentrated. Near the equator, it is softer and more diffuse. The first quiet payoff is that magnetism here is not only a direction in space, it is an energy reservoir shaped by tension. A magnetar is an ultra-dense stellar remnant with an extreme magnetic field. In that region, the field presses on matter like a steady wind presses on tall grass. Blades lean the same way because the wind sets a preferred direction. Even stiff stems must share the burden of that push. That matters because the crust is stiff and the field beneath it can still drift. Drift is slow enough to feel like stillness, yet the drift loads the shell the way tide and current load a rocky shore. A second visual anchor settles near a pole. Curved arcs rise above the surface and loop back, forming a crown of faint paths. The crown is not a solid ring. It is a bundle of curves with a gradient in brightness strongest where the curves crowd together. Each curve marks a route that charged particles tend to follow. Some curves close tightly and return quickly, others reach farther out before bending back. The next payoff is that the shape of these curves carries stored energy. A twisted shape holds more energy than a relaxed one. A slight twist can persist for a long time, then it can unwind in a moment. The scale stays gentle but startling. The whole star is about 20 kilometers across, about the length of a long lake. Inside that small span matter is packed so tightly that a rigid outer shell can form. The shell is thin compared with the radius, yet it carries the load. It behaves as a single skin over a deeper interior that can rearrange without flowing like ordinary liquid. A physical detail becomes important here. Stress does not spread evenly across the skin. It gathers along narrow bands, and the bands branch into networks. Where two bands cross the pattern, sharpens into corners. Along those corners, the surface can rise into slight ridges or sink into shallow troughs. The pattern resembles dried ground after a long heat, but the cause is not drying. It is shear and compression driven by the magnetic field. A small unlock follows. When strain concentrates, a tiny slip can change the field above it. The slip might be no larger than a shift along one seam, yet the consequence can extend far into the surrounding space. Time provides the first scale shift. Stress accumulates over long, quiet spans. Release can happen in the span of a few heartbeats. The change is abrupt, like a ridge of ice that suddenly gives way under steady pressure. A third visual anchor moves along one of the seams. The seam brightens into a thin filament, then fades. The bright line curves and branches. It follows the same boundaries that hold the strain. The light does not come from burning material. It comes from energy released in the space just above the crust. That space holds a thin, charged gas that cannot ignore the field. Its motion is guided into spirals and arcs. If the arcs are twisted, the gas distribution changes with them. The flare begins when the magnetic geometry relaxes toward a simpler form. Another payoff arrives in plain language. A flare is a reordering of structure, not a surface flame. Heat and light appear because tension drops to a lower state. Light behaves as a messenger of that drop. It arrives first as very energetic radiation, then softens as the region cools. The brightening can be brief, yet it can dominate the output for that moment. A fourth visual anchor expands outward as a thin shell of light. It sweeps through nearby gas and lifts a faint afterglow that slowly dims. The afterglow is uneven. It is brighter where the gas is denser. It is fainter where the surroundings are thin. The next unlock is that the surroundings record the flare like a shallow imprint. Even when the outburst ends, the crust remains marked by the same seam network. The field remains strong and it continues to load the shell. Some seams stay quiet for long periods, others reactivate in short sequences as if the shell settles in steps. A fifth visual anchor holds on the limb of the star. The haze is slightly brighter where scattering is strongest. The edge looks crisp, yet the glow feathers outward into darkness. A limit of observation enters softly. The surface is too small to be resolved in detail across interstellar distance. No direct measurement can trace each seam or each arc. Only the timing of the brightness and the colour of the light provide indirect clues. Those clues are filtered by intervening gas that scatters and absorbs. During the brightest events, the signal can become so intense that fine structure is lost. During quiet spans, subtle changes can hide in noise. The limit of intuition follows. It is hard to picture a solid that is rigid and close to failure across a wide area. It is hard to picture a field that behaves like a material under tension. Yet the repeating pattern of calm strain and release points toward that picture. The section settles back into stillness. Between bursts, the magnetar cools and the field drifts on long time scales. The drift is gentle, but it never fully stops. Above the pole, the crown of curves remains faint and steady. Below, the crust holds its seams in silence. The path now turns backward toward the moment this compact remnant forms, because the birth squeeze sets the field's strength. From that birth, later cracking and flaring follow as a natural consequence of a tightly packed world. A magnetar's later silence begins inside a fast collapse that lasts only moments. The birth squeeze and the newborn spin concentrate magnetism until the field becomes extreme. At this distance, the first sign is not the star itself. It is a bright expanding cloud with a hollow centre. The cloud has a ragged edge. It shows filaments and knots like torn fabric drifting outward. The brightness is uneven. Some regions glow strongly, and others fade into thin haze. A dark point sits near the centre. It is small and steady. Around it, the inner debris forms a faint layered bowl. The first quiet payoff is that collapse does not simply shrink a star. It also gathers its invisible structure. Magnetic field lines are patterns in space. When a conducting fluid is squeezed, those patterns are squeezed too. The idea is simple in plain language. A wide sketch becomes a tighter sketch when the paper is crumpled. The same lines now sit closer together. In that region, matter conducts so well that the field is carried with it. This does not require a deliberate push. It follows from the way charges respond to motion. The result is that a modest pre-collapse field can become far stronger after collapse. A second visual anchor holds on the inner debris. Thin sheets of material overlap. The sheets form curved arcs with shadows between them. The shadows are not empty. They are cooler regions with less glow. The gradients in brightness show differences in density. Density matters because it sets how the collapse proceeds. A core collapses inward, while outer layers move differently. Shear appears between layers. That shear is a physical detail with consequences. It can wind magnetic patterns like thread winding onto a spindle. Each turn adds tension. Each added twist stores more energy. The next payoff is that twisting can amplify a field without needing a giant starting field. A twist that begins small can become tight when rotation is fast. Rotation is the second part of the birth. The newborn remnant spins quickly. Even if the spin slows later, the early phase can be decisive. A single number places the scale. The magnetic field can reach about 1 quadrillion gauss. That is about 1 trillion times stronger than Earth's surface field. Such strength is not felt as a push on ordinary matter from far away. It acts through charges and currents. Inside the remnant, it couples strongly to the moving conductive material. The scale shift is gentle but sharp. The remnant is only tens of kilometers across. The field structure reaches far beyond that. It shapes the space around the star over thousands of kilometers and more. A third visual anchor appears above the central point. The expanding cloud grows thinner with radius. The outer edge becomes a delicate rim. The rim shows small ripples. Those ripples trace instabilities as the blast meets surrounding gas. The inner region is calmer, yet inside the remnant motion is violent in a quiet way. Convection can stir the hot newborn interior. Convection is hot material rising while cooler material sinks. Like slow-rolling boil in thick syrup, it moves mass without splashing. When such motion occurs in a rotating conductor, it can act like a dynamo. A dynamo is motion that turns kinetic energy into magnetic energy. In a magnetar's birth, the dynamo can build a strong large-scale field. The payoff here is immediate. Extreme fields can be created during a brief early window. Later, the star cools and stiffens. It becomes harder to rearrange the interior on large scales. The strongest imprint is left early, then carried forward. A fourth visual anchor shifts to the remnant's center as the debris thins with time. The bright cloud becomes fainter. The dark point becomes more prominent. Around it, a weak glow forms a small halo. The halo is not a sign of calm inside. It is a sign that heat is escaping. Heat escape is slow compared with the initial collapse. That contrast is another scale shift. The birth collapse happens in seconds. The cooling and field evolution happen over years and longer. The magnetar becomes a long-lived object with a short-lived origin. A limit of observation enters softly. The collapse cannot be watched directly in detail across distance. The interior is hidden by dense matter and by the bright surrounding debris. Only indirect traces are available later. Those traces include how the star spins and how it slows. They include how it radiates in different bands. Yet these are partial clues. They require models to link present behavior to past formation. Even those models have limits. The strength and geometry of the birth dynamo depend on conditions that are not perfectly known. Small differences in rotation or internal layering can lead to different outcomes. The limit of intuition follows. It is difficult to picture a field building in a fluid that is both extremely dense and extremely hot. It is difficult to imagine a solid crust forming soon after, yet still being forced by a field rooted deeper down. Still, the sequence makes a coherent path. Collapse concentrates, rotation wins, convection organizes. The magnetic field becomes a long memory of the birth. A fifth visual anchor returns to the expanding cloud. The filaments stretch outward. They thin into threads. The center remains compact. In the surrounding space, the debris meets a thinner medium. A faint bow-like shape forms where the expansion compresses gas. Compression makes a brighter arc. Behind it, the glow fades into darker regions. The next payoff is that the environment can influence what is seen later without changing the core fact of the field. Some remnants remain dense and bright. Others fade quickly. In all cases, the central object carries the concentrated field. That field later presses on the crust as the star cools. The crust forms as the outer layers freeze into a rigid lattice. Once rigid, it resists slow magnetic drift. Resistance creates stress. Stress creates seams. The narrative now moves from birth to structure. The next step is to treat magnetism as a set of curves and tensions in space. Those curves connect the interior memory to the outer magnetosphere. From that connection, later cracking and flaring become a natural continuation. The space around a magnetar is structured even when it looks empty. Its magnetic field builds a magnetosphere that holds charged particles and stores twist. At this distance, a dim halo surrounds the star. The halo is not uniform. It forms a set of faint arcs that rise and return like petals arranged around a dark center. The petals are brighter near the surface, they fade outward into a thin mist. A sharp limb marks the boundary of the solid star. Just above that limb, the glow shows a steep gradient. It drops quickly with height. The first small payoff is that the field is not only a background. It is a framework that can be tightened and loosened. Magnetosphere means the region where magnetism controls charged particles. In that region, particles do not move freely across the field. They slide along curved paths. They spiral as they travel. The spirals tighten where the field is strong. They widen where it weakens. The field lines act like guide rails made of geometry, not material. A second visual anchor settles closer. The petal arcs merge into a braided fan. The fan has strands that cross without touching. Each strand curves smoothly. Some strands close back on themselves near the star. Some reach farther out before bending. The brightest strands sit where curvature is strongest. In those bends, motion concentrates. The next payoff is that curvature matters because it stores tension. Magnetic tension is the tendency of bent field lines to straighten. Straightening releases energy. Bent lines hold energy in their shape. That energy can stay stored if the environment supports it. The environment is a thin plasma tied to the field. The plasma carries electric currents. Those currents help maintain a twisted configuration. The twist is not a violent knot. It is a gentle shear that builds over time. The analogy is simple and quiet. A vine can be wound around itself and still look calm. The vine holds springiness in its twist. The twist can remain until a small shift lets it unwind. In the magnetosphere, the stored springiness is magnetic. A third visual anchor moves outward to a larger scale. Farther from the star, the fan of strands becomes a faint wide dome. The dome is almost invisible. It shows a soft edge where glow scatters and fades. Within the dome, brightness is patchy. It forms bands that drift slowly with rotation. Some bands are narrow, some are broad. The physical detail is that the glow has a boundary. It does not extend smoothly without end. It becomes too thin to radiate efficiently. The next payoff is that this boundary can change with stress. When twist increases, the radiating region thickens. When twist relaxes, it thins. A single number places the scale. The magnetosphere can extend about 10,000 kilometers. That is similar to Earth's diameter. The star at the center remains only tens of kilometers wide. The scale shift is gentle. A compact object governs a volume far larger than itself, yet the control is not absolute everywhere. Far out, the field weakens. Other influences begin to matter. Closer in, the field dominates. Light behaves as a tracer of this dominance. Where the field is strongest, particles are guided into tight paths. Those paths produce harder radiation. Where the field is weaker, motion spreads and softens. A fourth visual anchor returns to the near region above the crust. The strands there are denser. They form a lattice of loops. Between loops, darkness appears like narrow gaps. The gaps shift with rotation. The gaps are not holes in space. They are places where fewer particles radiate. The next payoff is that the magnetosphere is not static. It breathes through slow rearrangement. Rotation sweeps the loop pattern around like a lighthouse beam, but without a physical beam. The variation is a geometry effect. Some directions show more radiating strands, some show fewer. Over longer time, the overall pattern changes as twist is added or removed. Twist is added when the crust below shifts slightly. Twist is removed when the field relaxes. This link is the quiet bridge between surface and space. Another scale shift enters through time. Rotation can be seconds. Crust loading can be years. Magnetospheric relaxation can be fractions of a second during a flare. The same structure spans all these rates. It can be almost still. Then it can move quickly. A fifth visual anchor forms as a subtle wave runs along the strands. The wave is seen as a ripple in brightness. It travels outward along a loop, then reflects back. The loop's brightness rises and falls. The edges of the ripple stay smooth. The next payoff is that information moves along the field. A disturbance at the surface does not need a moving object to travel. It travels as a change in the field and plasma state. That travel can redistribute energy quickly within the inner magnetosphere, yet it does not always escape. Strong fields can confine hot plasma close to the star. Confinement produces a compact glowing region. That region has a sharp inner boundary near the surface. It has a softer outer boundary where particles thin. A limit of observation enters softly. The field lines cannot be seen directly. The arc pattern is inferred from how brightness changes with rotation. It is inferred from how the spectrum hardens and softens. Different field geometries can produce similar signals. That creates a modelling ambiguity. It is a limit of inference, not a limit of effort. Even perfect timing can leave multiple solutions. The limit grows during the strongest outbursts. Extreme brightness can wash out fine structure. In quiet phases, faint signals can be lost in background. The limit of intuition follows. It is difficult to imagine tension in empty space. It is difficult to accept that a shape can store energy without a solid spring. Yet the magnetosphere behaves like a system that prefers simpler configurations. It resists excessive twist. It holds twist until a threshold is passed. Then it relaxes toward a lower strain state. That relaxation is the quiet core of magnetar activity. A final visual anchor slows the scene. The petal dome is seen again, now fainter. The strands align more smoothly. The glow becomes less patchy. A gentle transition begins. As the magnetosphere evolves, the crust beneath it must carry the counterforce. The next step moves inward. It follows the solid shell and its layered structure where stress concentrates into seams and slowly prepares the next release. A magnetar's brightness rests on a thin solid shell that hides an exotic interior. The crust is a layered lattice that resists motion, and that resistance turns slow magnetic drift into stress. At this distance, the star's edge is sharply drawn. Just inside that edge, the surface shows faint banding. The bands run like long, shallow ridges. Between them lie narrow troughs that catch less glow. A shadowed gradient appears near one region as if the surface sinks slightly there. The first small payoff is that the crust is not a smooth ball. It is a structured skin with preferred lines where strain collects. Crust means a rigid outer layer made of dense nuclei. The layer is thin compared with the radius. Yet it carries shear like a shell of ice on a deep lake. When the lake swells, the ice cannot stretch much. It forms cracks and pressure ridges. In a magnetar, the deeper material does not swell like water. It shifts under magnetic forces and cooling. That shift is slow. The crust must accommodate it anyway. The next payoff is that slow change can be more damaging than fast change. Fast change can bounce and settle. Slow change can keep loading the same weak places. Primary visual anchor appears as a cutaway through the outer kilometers. The outermost layer looks like tightly packed beads in a regular grid. Deeper down, the beads stretch into rods. Deeper still, the rods merge into sheets. The shapes form a layered texture with clear boundaries. Each boundary is a change in density and arrangement. These boundaries matter because they scatter strain. Some layers slide more easily, some lock together. The physical detail is that strain concentrates at interfaces. It becomes highest where a stiff layer meets a softer one. Those regions become natural fault zones. The analogy is quiet and familiar. A stack of thin, dry pastry sheets bends differently than a single thick loaf. When pressed, the stack shifts in steps. Small slips happen between layers. Each slip releases a little stress. That matters because the crust may not fail in one clean break. It can adjust in a series of tiny rearrangements. Each rearrangement changes the magnetic footprint above it. A single number places scale. The crust is about 1 kilometer thick. That is like the depth of a deep canyon. On a star only tens of kilometers wide, this is a thin skin. Yet that thin skin governs what the magnetosphere feels. The scale shift is gentle. A kilometer is small compared with a planet. Here it is a defining boundary between solid behavior and deeper strange matter. The next payoff is that thickness sets the tone of failure. A thicker shell can store more elastic energy. A thinner shell can crack more readily. Either way, the key is that the crust is strong but not infinite. Strength is not only about breaking, it is about resisting shear without permanent change. When the magnetic field below drifts, it pushes sideways on the base of the crust. Sideways push is what makes faults. A second visual anchor returns to the surface. A network of hairline seams forms a web. Some seams are nearly parallel, others intersect at sharp angles. Along one seam, the surface shows a subtle step like a tiny cliff only centimeters high. That step casts a narrow shadow. The shadow shifts with rotation. The next payoff is that even tiny steps signal large forces. The crust is dense and stiff. Moving it takes immense stress, yet the motion can still be small. The field does not need to shift the whole surface. It needs only to move enough to change currents above. That is why small geometric changes can yield large radiative changes. A third visual anchor holds on a region where the seams curve. The curvature tightens into a hook shape. The hook marks a place where stress might be pinned. Around it, brightness is slightly higher, not because material is hotter there by default. It is higher because currents concentrate along that seam line. Concentrated currents heat the near-surface plasma. Heating makes harder emission. The connection is quiet but direct. Geometry guides current. Current guides glow. A limit of observation enters softly. The crust cannot be mapped directly in fine detail from far away. The star is too small for surface imaging. Inferences come from timing and spectrum. Those are integrated signals. They average across the whole visible face. That means many different seam patterns can produce similar changes in light. Models help, but they are not unique. Another limit appears during active episodes. The magnetosphere can become bright enough to veil surface contributions. That veiling is an observational limit. It hides the crust under its own reactive atmosphere. The limit of intuition follows. It is hard to picture a solid that holds under enormous gravity, while also being brittle enough to crack. Gravity presses everything down. In everyday life, pressure can make solids flow slowly. Here, pressure and quantum structure allow a stiff lattice to exist. The lattice resists shear up to a point. Then it slips. The slip can be sudden, yet the cause can be a slow drift over years. A fourth visual anchor provides a calmer scale shift. Heat leaves the star gradually. The temperature gradient through the crust changes slowly. The outer surface cools first. The deeper layers cool later. Cooling changes the lattice stiffness. It also changes how easily magnetic patterns move through the crust. This creates an evolving balance. In one epoch, stress builds more at shallow depths. In another, it builds deeper. The next payoff is that cracking behavior can change with age. Younger objects may show frequent small adjustments. Older ones may store stress longer and then release in rarer events. The crust acts like a gate. It does not create the energy. It decides how the energy is released. A fifth visual anchor returns to the cutaway. A thin band at the base of the crust looks slightly mottled. The mottling represents regions where magnetic field strength varies. Where the field is stronger, the push on the lattice is stronger. Where it is weaker, the lattice can relax. The boundaries between strong and weak regions become natural sites for shear. Those boundaries are like seams in fabric. Fabric does not tear anywhere at random. It tears along a line of weakness or along a stitched edge. In the crust, the stitched edges are density and composition transitions. The final payoff is that the Magnetars' most dramatic events are prepared quietly by these edges. A small slip at one boundary can twist magnetospheric loops. A larger slip can trigger a broader reconfiguration. The section ends with a gentle transition. The crust now appears as a loaded shell with a web of seams. The next step follows what happens when that web cannot hold and a slip becomes a starquake, sending a rapid churn upward into the magnetosphere. A crust can hold for a long time, then yield in a single quiet slip. A starquake is a sudden crust shift that transfers stress upward into the magnetosphere. At this distance, the surface seems unchanged, yet a fine seam brightens and darkens in a slow pulse. The seam runs across a shallow ridge. It meets another seam at a sharp angle. At the junction, a tiny step casts a thin, moving shadow. The first small payoff is that a quake does not need a large crack to matter. It needs a change in alignment. Alignment is what the magnetic field cares about. Starquake means a rapid fracture or slip in the solid crust. The slip is not a collapse. It is a shear that relieves built-up strain. Like a stuck drawer that suddenly sideways when pressure reaches a threshold. The crust releases motion that was waiting. The drawer moves only a little. The relief is immediate. That matters because the magnetosphere is coupled to the crust. When the crust shifts, the foot points of magnetic loop shift too. The loops above are anchored at the surface. Their anchoring points move by a small distance. The loop geometry changes. Even a small change can increase twist or reduce it. A second visual anchor holds on the moment just above the surface. A bundle of arcs rises like a low dome. The dome is brighter on one side. It is dimmer on the other. A narrow dark lane runs through the glow, marking where fewer particles radiate. When the surface slip occurs, the dark lane bends. It becomes a soft S-curve. The brightness on one side sharpens. The next payoff is that the magnetosphere responds faster than the crust ever can. The crust shift is brief. The magnetosphere rebalances almost immediately. The response looks like a ripple of brightness that runs along the arcs. It travels outward and then returns. The ripple is not a moving object. It is a change in field and plasma state. Light behaves as a record of that change. Some energy goes into heating particles. Some goes into reorganizing the field. A primary number places the timescale. The slip can unfold in about 1 second. That is similar to the time of a single deep breath. The scale shift is gentle. A process loaded over years resolves in a second. That contrast helps explain why magnetars can seem quiet and then suddenly flare. The crust is a slow accumulator. The quake is a fast release. A third visual anchor moves across the surface seam network. Several seams brighten in sequence. The sequence moves like a wavefront. It starts at the junction. It then branches along 2 directions. The bright lines fade behind the front. The next payoff is that quakes can cascade. One slip can load a neighbouring seam. The neighbour may already be close to failure. It then slips too. The cascade looks like a patterned settling rather than a single tear. This is important because it shapes how energy is distributed. A single dominant rupture can pump a large twist into one set of loops. A distributed cascade can spread smaller twists across many loops. Both outcomes change the magnetosphere's stability. The analogy is quiet and specific. A row of standing books can remain still until one shifts. The shift presses the next. The line adjusts in a gentle chain. Each movement is small. The whole row finds a new arrangement. In the crust, the books are fault blocks and lattice domains. The pressure is magnetic stress and elastic strain. The new arrangement is a new geometry for field anchoring. A fourth visual anchor appears farther out. The inner dome of arcs thickens into a brighter sheath. The sheath has a sharp inner boundary near the surface. It has a softer outer boundary where glow thins. Within it, brightness shows a gradient. It is brightest where the field curvature is greatest. The next payoff is that heating is localized. The quake injects energy at specific foot points. Currents intensify along certain loops. Those loops glow, other loops remain faint. This selectivity is why magnetar activity can appear patchy. It is also why repeating activity can occur in the same general region. The crust has preferred seams. The magnetosphere has preferred loops anchored there. A limit of observation enters softly. The crust slip itself is not seen directly. The surface cannot be resolved. The quake is inferred from timing changes, from brief spectral hardening, and from changes in pulse shape as the star rotates. These are indirect clues. They depend on models of loop geometry. Different quake patterns can produce similar light curves. That is a limit of inference. Another limit appears in the strongest events. Radiation can saturate the signal. Fine timing structure can be lost. The exact sequence of slips becomes uncertain. The limit of intuition follows. It is difficult to imagine a solid crust under immense gravity moving at all. It is also difficult to imagine that tiny shifts can power intense bursts, yet the key is stored energy. Energy is not created by the slip. It is released by allowing the field to relax or to reconfigure. The crust is the trigger. The field is the reservoir. A fifth visual anchor returns to the seam junction. After the slip, the shadowed step remains. The seam looks slightly offset. The glow above it calms. The arcs regain a smoother shape. The magnetosphere is quieter but not identical to before. A small unlock settles the scene. Each quake slightly changes the long-term stress map. Some regions become less loaded, others become more loaded. Over time, the system explores many near-stable states. The story now moves from the trigger to the main release process. If a quake injects enough twist, the field can abruptly rearrange in the outer region. That rearrangement can convert stored tension into a giant flare. The next section follows how twisted arcs can snap toward a simpler shape and release energy as a brief intense flash. A giant flare begins as a quiet decision of geometry when a twisted magnetic shape relaxes toward a simpler one. The main release happens when stressed field lines reconnect and shed stored tension as light and heat. At this distance, the magnetar looks unchanged until a single hard flash rises from its vicinity. The flash is not broad, it is compact and sharp. It is followed by softer glow that lingers. Near the star, a thin, bright arc forms above the surface like a narrow ribbon. The ribbon sits just off the limb. It traces a curve that is brightest at its midpoint. The first small payoff is that the flare is not a surface fire. It is a rapid rearrangement of magnetic structure in the space above the crust. Reconnection means magnetic field lines change partners and reduce twist. The idea stays simple. Lines that were bent and crowded become less bent and less crowded. In that region, the plasma is thin but conductive. It carries currents that support the twisted shape. When the shape can no longer hold the current shift, the field snaps into a lower strain configuration. The energy difference appears as radiation. A visual anchor settles on the arc ribbon. It fractures into two brighter knots at its ends. Between the knots, the glow thins into a dim lane. The lane is a physical boundary where fewer particles radiate. The next payoff is that boundaries matter. Reconnection concentrates in thin layers. Those layers are narrow compared with the magnetosphere, yet they control the release. A second visual anchor moves outward. Above the ribbon, a fan of faint loops straightens. The loops do not disappear. They become smoother. Their curvature decreases. Where the curvature decreases, tension drops. Where tension drops quickly, particles are accelerated. Light behaves as a direct trace of that acceleration. The earliest radiation is hard, comes from particles forced into rapid motion. The glow then softens as energy spreads and the region cools. The main number places the tempo. The initial spike can last about 1/10 of a second, that is shorter than a heartbeat. The scale shift is gentle but decisive. Years of slow loading can discharge in a fraction of a second. The crust is not moving for that whole time. The crust supplies the trigger and the anchoring. The magnetosphere supplies the fast response. A payoff arrives in plain terms. The flare is a release valve for magnetic stress. The crust can only slip in limited ways. The magnetosphere can reorganize quickly once a threshold is crossed. A third visual anchor forms in the surrounding space. A thin shell of scattered light expands into nearby gas. The shell is not a solid wall. It is a faint ring with a bright inner edge and a softer outer edge. The brightness shows a gradient. It is strongest where gas density is higher. It fades where the environment is thin. The next payoff is that the surroundings become a soft screen. They reveal the flare's reach without showing the exact mechanism. The light front moves outward. Behind it, the space near the star remains bright. That brightness can persist as trapped plasma. Trapped plasma means hot charged particles held by strong magnetic loops. The loops act as a closed container of geometry. The container has an inner boundary near the surface where the field is strongest. It has an outer boundary where the field weakens and particles escape. A fourth visual anchor holds on this trapped region. It looks like a glowing cap above one hemisphere. The cap has a sharp lower edge. The edge follows the curve of the star. Above the edge, the glow becomes mottled. It shows patches of brighter emission and patches of dimmer emission. The next payoff is that the flare is not a single moment. It has phases. The first phase is the spike that announces reconnection. The second phase is the trapped glow that cools and gradually fades. Cooling happens by radiation and by gradual leakage. The glow can pulse with rotation. Some directions show more cap area. Some show less. A fifth visual anchor returns to the near field lines. The loops that remain twisted are now fewer. They gather into a simpler crown. The crown has wider spacing between strands. The gaps are darker. The next payoff is that reconnection reduces complexity. Complexity stores energy. Simplicity releases it. The analogy stays natural and unique. A braided river can carry its flow through many intertwined channels. After a flood, the channels can cut new paths. Some braids are abandoned. The flow becomes straighter in places. The landscape did not gain new water. It rearranged the same water into a new pattern. In the magnetosphere, energy is not added at the flare. It is rearranged. The field takes a shorter path through configuration space. The energy difference becomes light. A limit of observation enters softly. The reconnection layer is far too small to be resolved directly. The spike is so bright that fine timing structure can be distorted. Scattering an intervening gas can smear the signal into a halo. That smearing hides the earliest sharp features. Even the spectrum can be modified by absorption on the path. Models can reconstruct likely geometries, but multiple geometries can fit similar light curves. This is a limit of inference and of resolution. The limit of intuition follows. It is difficult to picture a process that acts like a switch without a physical lever. Yet the switch is a threshold in stability. A twisted field can sit in a stressed state for a long time. It can be held by currents and by anchoring to the crust. Then a small change in anchoring can push it past a boundary. Past that boundary, the simplest path is rapid relaxation. A sixth visual anchor calms the scene as the afterglow fades. The cap above the star thins, its sharp edge softens. The mottled patches merge into a smoother dim halo. The expanding ring in the surrounding gas becomes faint. It blends back into darkness. The next payoff is that the system rarely returns to the exact prior state. The magnetosphere now carries a new distribution of twist. Some regions are calmer. Others still hold strain. The crust below remains a loaded shell. Slow drift resumes. This sets the stage for smaller releases that repeat. The next section follows how bursts can occur in clusters where the system relaxes in steps instead of one complete discharge. After a giant flare, the magnetosphere often settles by releasing stress in smaller steps. Repeating bursts are short magnetic relaxations that drain twist without emptying the reservoir at once. At this distance, the star returns to a quiet point, yet the quiet is punctuated by brief flickers. Each flicker rises fast and fades softly. Between flickers, the steady glow looks slightly different. It shifts in hardness and in pulse shape as the star rotates. A primary visual anchor forms close to the star. A set of loops creates a bright crescent above one limb. The crescent has a sharp inner edge. It hugs the surface like a thin line of frost. Above it, the glow spreads into a shallow fan with a smooth gradient. The first small payoff is that bursts can be a controlled discharge. They can be the system stepping down from a more stressed state to a less stressed one. A burst is a brief release of magnetic energy in the magnetosphere. It does not require the whole field to reorganize. It can occur in a limited bundle of loops. The trigger can be a small crust slip or a gradual drift that reaches a threshold. The result is a short spike of radiation, then a quick return toward baseline. The analogy is quiet and unique. A drying sponge can hold water unevenly. A slight squeeze releases a few drops. The sponge remains wet. Repeating squeezes produce repeating drops. In the magnetar, the sponge is the twisted field. The drops are bursts. The field remains strong and structured. Only a portion relaxes at each step. That matters because it explains clustering. When one bundle relaxes, neighbouring bundles may be brought closer to their own threshold. A second visual anchor follows the loops during one burst. The crescent brightens into a bead-like chain. Several beads appear along the arc, separated by dim gaps. The gaps mark places where fewer particles radiate. The beads mark places where curvature and current concentrate. The next payoff is that bursts reveal where stress lives. Stress is not spread evenly, it gathers where loops are tight and where anchoring is complex. In that region, particles are accelerated more efficiently. Light behaves as a tracer of current pathways. Small change in geometry redirects those pathways. The emission pattern shifts. A single number places the pace. Bursts can repeat dozens of times in an hour. That is like soft rain tapping a surface again and again. The scale shift is gentle. The loading that prepares these taps takes far longer than the tapping itself. Slow drift in the crust and deeper field supplies the pressure. Fast magnetospheric adjustment produces the flashes. A third visual anchor moves outward into the near environment. Each burst sends a faint expanding ripple into surrounding gas. The ripple is not always visible. When it is visible, it forms a thin ring-like edge. The edge is brighter where gas density is higher. It is fainter where the medium is thin. The next payoff is that the environment can act as a memory. It can collect the sum of many small events into a subtle glow. Even if each burst is short, the repeated energy deposition can keep a faint halo alive. That halo is a physical detail with a boundary. It fades beyond a certain radius because the gas becomes too thin to radiate. A fourth visual anchor returns to the star in its rotation. As the star turns, the bright crescent moves in and out of view. Its inner edge remains sharp. Its outer fan remains soft. During a burst, the fan thickens. It becomes brighter and more mottled. After the burst, it thins again. The next payoff is that bursts change the magnetosphere's optical depth and particle density. The system briefly becomes more opaque to its own radiation. Then it clears. This can shift which energies escape most easily. The effect is seen as a temporary hardening or softening of the spectrum. It is also seen as a change in pulse fraction. These are not separate mysteries. They are different faces of the same adjustment. A limit of observation enters softly. Individual bursts are easy to time but harder to interpret uniquely. The light curve is a sum over many regions. Multiple loop bundles can flare nearly together. Their signals overlap. Scattering in interstellar dust can smear sharp features into broader tails. That smearing is a limit on time resolution. It blurs the true rise time and can mimic slower physics. Another limit is geometric. The orientation of the magnetar relative to the observer affects which regions dominate. A burst on the far side may be partly hidden. The true energy then must be inferred. That inference depends on models of beaming and absorption. The limit of intuition follows. It is difficult to picture how a structure can relax in many tiny jumps instead of one decisive release. Yet the magnetosphere is large and inhomogeneous. Different bundles carry different twist. Different anchors in the crust drift at different rates. A threshold reached in one bundle does not guarantee a threshold everywhere. The system therefore steps down unevenly. Each step is small. Together they can reshape the overall pattern. A fifth visual anchor focuses on a boundary between two loop bundles. The boundary appears as a dim lane between two brighter fans. During a cluster, the dim lane brightens briefly, then it darkens more than before. The next payoff is that boundaries can migrate. When one bundle relaxes, twist can be transferred outward or inward. The dim lane marks where currents were reduced. It is a sign of partial unloading. This partial unloading can quiet the system for a time. It can also leave residual twist in deeper or adjacent regions. Over longer time, the drift resumes. Stress rebuilds. The clustering can return. The section closes by easing toward the next mechanism. Repeating bursts suggests that the magnetosphere holds multiple stable configurations. It can move among them by small reconnection events. The next step goes deeper into how trapped plasma and radiation can linger, after activity, forming a hot confined region that cools and fades without escaping freely. After the brightest activity part of the energy remains close to the star as a trapped fireball that cools in place. Strong magnetic loops confine hot plasma and radiation into a compact region with clear edges. At this distance, the flare is already past. A softer glow remains and turns with the star. The glow looks like a cap above one hemisphere. Its lower boundary is sharp. It hugs the limb like a thin, bright border. Above that border, the cap becomes mottled. Bright patches sit beside dim patches. The first small payoff is that the afterglow is not merely leftover heat on the surface. It is a confined cloud suspended by magnetic geometry. Trapped fireball means a hot, dense mix of light and charged particles held by field lines. In that region, particles cannot easily cross the field. They slide along loops and bounce between mirror points. Radiation scatters repeatedly within the cloud. That repeated scattering keeps energy local for a time. The plain picture is simple. A valley can hold fog when the air is still. The fog is not glued to the ground. It is held by the shape of the land and by stable conditions. In the magnetosphere, the valley is a set of closed loops. The fog is plasma and radiation. The hold lasts until cooling and leakage thin the cloud. That matters because it creates a second phase to magnetar outbursts. The spike is brief. The trapped phase can persist longer and pulse with rotation. A primary visual anchor settles on the cap boundary. The boundary is not a smooth circle. It has a scalloped edge. Small indentations and bulges appear along it. Each bulge marks a cluster of loops with stronger confinement. Each indentation marks a region where confinement is weaker. This physical detail is important. The boundary is a map of magnetic topology. Where the field is more closed and curved, the cloud is thicker. Where the field opens or weakens, the cloud thins. The next payoff is that the fireball cools from the outside inward. The outermost layer radiates first. It becomes more transparent as particles thin. As it clears, deeper layers become visible. The cap therefore changes shape with time. The mottled patches drift and soften. The sharp border becomes less sharp. A second visual anchor moves inside the cap. A bright knot forms near one edge. It looks like a small ember. It fades slowly rather than flashing. The ember sits where loop curvature is high. Curvature raises magnetic tension. It also supports stronger currents. Currents can heat particles and maintain opacity. The next payoff is that opacity controls the cooling rate. Where scattering is strong, energy takes longer to escape. Where scattering is weaker, energy leaks faster. This creates a natural pattern of slow and fast fading within the same cap. A single number places the scale of persistence. The trapped phase can last about a few minutes. That is like the time it takes for a kettle to cool from hot to warm in still air. The scale shift is gentle. The flare spike lasts a fraction of a second. The trapped glow lasts minutes. The crust loading that prepared it lasts years. 3 timescales nest inside one another without conflict. A third visual anchor shifts outward to the loops that hold the cap. The loops form a cage of arcs. The cage has a denser inner region and a sparser outer region. The inner region has closely spaced strands. The outer region has larger gaps. The gaps are darker lanes. The next payoff is that leakage happens at the gaps. Where loops are more open, particles can escape along paths that reach far out. Where loops are closed, particles remain trapped and cool locally. This balance sets how the cap fades. It also sets how the emission spectrum evolves. Early in the trapped phase, emission is harder. Later it softens as the cloud cools and as scattering becomes less intense. Light behaves as a thermometer here. It is not a thermometer with a direct scale. It is a tracer of changing opacity and temperature. A limit of observation enters softly. The cap is not seen as a resolved shape. Its presence is inferred from pulsed emission and spectral evolution. Many different cap geometries can produce similar pulse profiles when integrated over the whole visible region. Orientation adds another uncertainty. If the cap sits near a pole aligned with the rotation axis, pulses can be weak. If it sits off axis, pulses can be strong. This is a limit of geometry. It is also a limit of inference. Models can reproduce the data, but they may not uniquely determine the cap's size and location. Another observational limit appears in scattering by surrounding dust. Dust can create a halo that adds delayed light, smoothing sharp features in the afterglow. The limit of intuition follows. It is difficult to imagine radiation trapped as if it were a fluid. In everyday life, light escapes quickly. In a dense, scattering cloud, light takes a long random walk. It bounces many times before leaving. That random walk can make minutes out of a small region. It can make the afterglow feel steady even as energy drains. The next payoff is that confinement makes the system gentler. Instead of all energy leaving at once, some is released slowly. This slow release reduces abruptness in the overall light curve. It also allows the magnetosphere to settle gradually. A fourth visual anchor returns to the scalloped boundary, now softer. The indentations blur. The bright border fades into a wider gradient. The ember knot dims and merges into the background. The cap becomes a faint halo. The halo's edge continues to retreat toward the star as cooling proceeds. The section closes with a quiet transition. As the trapped cloud thins, the magnetosphere becomes less loaded with plasma. That changes how later bursts propagate and how field lines carry currents. The next section follows how vibrations and oscillations can appear after strong activity, imprinting subtle rhythms on the fading glow without requiring new outbursts. After a strong outburst, the fading light can carry a faint rhythm like a slow pulse beneath the main pulse. Quasi-periodic oscillations appear when the crust and magnetosphere vibrate together and modulate the emission. At this distance, the afterglow seems smooth until its brightness shows a subtle tremble. The tremble is not random. It repeats with a steady spacing for a short time. The steady spacing rides on top of the rotation signal. A primary visual anchor forms as a close view of the surface seam network. A broad ridge crosses the crust. Along it, several hairline faults run parallel. Between faults, the surface looks slightly corrugated. The corrugations are shallow waves. Their crests catch more glow. Their troughs hold a thin shadow. The first small payoff is that the star can ring like a bell without making sound. It rings by shifting stress in solid layers and in the attached magnetic loops. Oscillation means repeated motion around an equilibrium state. In this case, the equilibrium is a stressed crust plus a structured magnetosphere. The motion can be a torsional mode, which is a twisting of the crust around the star's axis. The definition stays short. A torsional mode is a shear wave that twists the crust. The picture becomes plain. A thick rubber disc can be twisted and released. It does not shatter. It returns toward its resting shape and overshoots. It repeats. That matters because the crust's twist can tug on magnetic foot points. When foot points move back and forth, the magnetospheric currents change back and forth. When currents change, emission changes. The rhythm in light is therefore a signature of coupled motion, not a separate engine. A second visual anchor moves to the magnetosphere just above the corrugated ridge. A bundle of loops rises like a low canopy. The canopy is brighter where loops are tight. It is dimmer where loops are spaced. During vibration, the canopy does not move as a whole. Instead, brightness slides along it in bands. A bright band travels upward along the loops and then fades. A dim band follows. The next payoff is that modulation can occur without changing total energy much. The light is redistributed in phase with the vibration. This makes the signal rhythmic even if the overall afterglow still fades. The primary number places the rhythm. The tremble can be around 30 cycles per second. That is like the hum of a low note in the air, steady and quick. The scale shift is gentle. The crust loads for years. The flare releases in fractions of a second. The vibration rings for seconds to minutes and then damps out. 3 time scales sit together. Each has its own physics. The vibration damps because energy is converted into heat and radiated away. It also damps because the magnetosphere and crust are not perfect springs. They have internal friction and leakage. A third visual anchor holds on the boundary between 2 crust layers in a cutaway. The outer lattice looks like tight beads. Beneath its shapes stretch into rods and sheets. The boundary is a clear line where properties change. During a torsional wave shear is concentrated near certain depths. Some layers slide a little relative to others. The next payoff is that layering selects which modes are strong. A thick, stiff layer supports different frequencies than a thinner, softer layer. Coupling to the magnetic field also matters. Stronger field coupling can shift the effective stiffness. This helps explain why the observed rhythm can drift slightly. It is not always fixed. It can change as the magnetosphere empties of plasma and as currents relax. A fourth visual anchor returns to the afterglow cap. The cap's scalloped edge from earlier phases is now faint. Yet the edge shows a subtle breathing. It expands a little and contracts a little in brightness. The shape does not fully change, only the intensity pattern shifts. The next payoff is that the cap acts like a lampshade for vibration. The vibration changes where the cap is most opaque. That changes which parts shine through most strongly. The observer sees a changing mask. The mask oscillates at the crustal mode frequency. Light behaves as the messenger of that mask. A limit of observation enters softly. The rhythm is small compared with the main signal. It can be lost if noise is high. It can be smeared if scattering and intervening dust creates delayed light. It can also be confused with instrumental effects if the sampling is coarse. This is a limit of time resolution and of signal to noise. Another limit is degeneracy. Different mode patterns can produce similar intensity modulations once averaged over a rotating star. Without direct spatial resolution, identification relies on matching to models. Those models depend on uncertain crust composition and magnetic geometry. This is a limit of modelling. The limit of intuition follows. It is hard to imagine a star's crust twisting without tearing itself apart. Yet the motion can be small in amplitude and still visible in light. Even slight footpoint motion can change currents. Currents can change emission efficiently. The star can therefore ring in a subtle way that is easier to see than to picture. A fifth visual anchor shows the end of the ringing. The corrugations on the ridge appear to smooth out. The shadowed troughs become less distinct. Above the canopy bands fade. The afterglow resumes a more monotonic decline. The next payoff is that the end of oscillations marks a settling of the coupled system. The crust finds a quieter stress distribution. The magnetosphere loses some of its trapped plasma and becomes clearer. With less plasma, later bursts may propagate differently. With less twist, the system may become more stable for a time. The section eases toward the next step. The vibrations have shown that solid structure and magnetic structure are linked. The next section widens the view to longer timescales, where slow cooling and gradual magnetic drift reshape the star's behaviour across years and beyond. A magnetar changes most in the long quiet intervals between outbursts. Cooling and slow magnetic drift reshape the crust and magnetosphere over years, setting the timing of future activity. At this distance, the object is steady. Its pulse repeats with calm regularity. The spectrum slowly softens. The halo becomes thinner. A primary visual anchor forms as a wide view of the star's surface under low light. The surface shows broad zones with different brightness. One zone looks slightly warmer. Another looks cooler and darker. The boundary between them is a curved band. Along that band, faint seams align like grain in wood. The first small payoff is that the long-term story is written in gradients. Temperature gradients and field gradients decide where stress accumulates. Cooling is the outward flow of heat from the interior. It is not a uniform flow. Heat travels through layers with different conductivity. It also travels through a crust that is threaded by magnetic structure. In that region, the magnetic field can guide heat along preferred directions. The result is a patterned surface temperature. Patterned temperature means patterned stiffness. Stiffer regions resist shear more strongly. Softer regions accommodate drift more readily. That matters because stress will not build everywhere equally. It will build where drift meets resistance. A second visual anchor moves to a cutaway of the outer layers. The crust shows a smooth temperature gradient. It is warmer at depth and cooler at the surface. Within that gradient, there are thin interfaces where composition changes. Those interfaces are marked by subtle colour shifts in the imagined cutaway. The next payoff is that interfaces act like speed bumps for both heat and magnetic evolution. Heat can be slowed or redirected by changes in conductivity. Magnetic patterns can move more easily in some layers than others. When movement is uneven, shear develops. This shear is a slow kind of loading. It is quiet. It still matters. The core concept is magnetic drift in conducting matter. Drift means the field configuration changes gradually through the crust and outer interior. The change can be driven by diffusion and by motion of charged components. It is not a rapid reconnection event. It is a gradual rearrangement that keeps the field mostly continuous. The analogy is simple and unique. Ink soaked into thick paper spreads slowly. The edge of the ink front advances. It does not jump. It follows the texture of the paper. In a magnetar, the paper is the crust and outer layers. The ink front is the slow change in field configuration and current distribution. That matters because slow spreading can still lead to sharp edges. Sharp edges form where properties change suddenly. Those edges become natural sites of future failure. A primary number places the long scale. Significant cooling and drift unfold over about 10,000 years. That is like the time span of a long geological era on Earth's surface, yet it is only an early chapter in cosmic time. The scale shift is gentle. Bursts last fractions of a second. Trapped afterglow lasts minutes. Stress rebuild lasts years. The overall evolution spans thousands of years. The object gradually moves from a highly active phase to a quieter phase as energy reservoirs decline. A third visual anchor returns to the surface boundary. The boundary slowly migrates across the star as internal conditions change. The bright zone shrinks, the dark zone grows. Along the migrating front, new seams appear while old seams fade. The next payoff is that the crust is not only damaged by dramatic quakes, it is also remodeled by slow creep and gradual adjustment. Creep here means very slow deformation under persistent stress. It is not a liquid flow, it is a gradual shift in the lattice and in fault boundaries. This can relieve some stress without bursts. It can also concentrate stress into narrower zones. When that concentration becomes sharp enough, a quake becomes more likely. A fourth visual anchor extends outward into the magnetosphere. The loop crown above the active zone is thicker. The strands are closer together. Above the quieter zone, the strands are sparser. The gaps are darker lanes. The next payoff is that magnetospheric loading mirrors crustal conditions. Where drift twists foot points more, the magnetosphere holds more current. Where drift is calmer, loops are closer to a relaxed shape. Over time, the average twist declines as the field seeks lower energy configurations, and as bursts drain stress. Yet the decline is not smooth, it can plateau, it can step. The system can linger in a near stable state and then shift. A limit of observation enters softly. Long-term evolution is inferred from sparse snapshots. No single magnetar is followed continuously across millennia. Age estimates are uncertain. They depend on models of spin down and on assumptions about the environment. This is a limit of chronology. It makes it hard to map a precise timeline for each object. Another limit is internal. The deep interior is hidden. The distribution of field between crust and core cannot be measured directly. Only surface emission and timing provide indirect constraints. Different internal configurations can yield similar external behavior. This is a limit of inference. The limit of intuition follows. It is difficult to hold two pictures together. One picture is a rigid crust that can crack suddenly. The other is a slow evolution over thousands of years. Both are true because the system has thresholds. Slow drift moves the system toward a boundary. Crossing the boundary produces a fast event. The fast event then resets conditions slightly. The next payoff is that magnetar activity is a natural consequence of a threshold-driven system. Calm does not mean empty. Calm can mean stored stress below the threshold. A fifth visual anchor settles into a broader galactic view without introducing human scale. The magnetar sits within a thin interstellar cloud. The cloud has faint wisps. A small cavity surrounds the star where past outflows have reduced density. The cavity edge is a weak shell. It is slightly brighter where it compresses gas. The next payoff is that the environment records the long-term balance. An active phase can maintain a cavity. A quiet phase lets the cavity soften as gas drifts back in. The magnetar does not need to be continuously explosive to shape its surroundings over time. The section ends with a gentle transition. The slow evolution has set the stage for subtle changes in how signals escape. The next section widens to consequences beyond the immediate magnetosphere, following how repeated activity and radiation can influence nearby gas and dust across larger regions and longer spans. A magnetar leaves marks on its surroundings even when the star itself looks like a quiet point. Repeated radiation and particle outflow can carve a faint bubble in nearby gas and light up dust as a soft echo. At this distance, the region around the star is not empty black. It has a thin mist of interstellar material. The mist shows wisps and lanes. A shallow cavity surrounds the magnetar. The cavity edge is a weak shell. It is slightly brighter along one arc, then fades into darker space. The first small payoff is that the environment becomes a diary. It records the cumulative influence of many small events and a few large ones. A primary visual anchor holds on the shell boundary. The boundary has a rippled texture. Small scallops run along it like a slow wave frozen in place. The inner side of the shell is dimmer. The outer side is brighter where compression is higher. The physical detail is a density gradient across the shell. Compression raises density. Higher density radiates more. Lower density radiates less. This gradient makes the shell visible as a soft rim instead of a solid ring. The next payoff is that a magnetar can shape gas without a continuous blast. Short bursts can still deliver energy. They can heat and ionize nearby material. Over time, repeated inputs maintain a cavity against slow refill by ambient gas. The cavity can be asymmetrical. It depends on the local density. It also depends on where energy is deposited most effectively. A second visual anchor shifts to dust near the star. Dust grains form a faint veil. The veil brightens after an outburst, then fades. The brightening appears as a broad halo. The halo has a smooth inner region and a softer outer region. Its edge is not sharp. It is a gradual fall off, like fog thinning with distance. The next payoff is that dust can delay and scatter light. A burst can produce a halo that appears later and grows in apparent size. This creates an echo in light. The echo does not require the magnetar to keep shining strongly. It requires only that light from the outburst take different paths. Some paths are direct. Some paths scatter off dust and arrive later. Light behaves as if it has a memory in dusty space. A primary number places the scale of the cavity. The bubble can be about 1 light year across. That is about the distance light travels in 1 year. Compared with the star's tens of kilometers, this is an enormous reach. The scale shift is gentle. A compact object influences a region trillions of times larger in linear size. Yet the influence is not a force pushing a wall. It is a long history of heating and pressure changes. It is a sequence of small nudges. A third visual anchor shows a filament crossing the bubble edge. The filament is a denser lane. It bends slightly as it meets the shell. The bend creates a bright knot where compression is strongest. The next payoff is that the surrounding medium is not uniform. Dense filaments act like obstacles. They focus the interaction into knots and arcs. This can make the bubble look irregular. It can also concentrate emission into patches rather than a smooth circle. A fourth visual anchor returns to the halo from dust scattering. The halo's brightness is not uniform. It forms faint concentric bands. The bands are broader near the center and thinner farther out. The next payoff is that banding can arise from dust distribution. If dust is clumped into layers, scattering produces rings of enhanced brightness. These rings are not solid structures. They are a projection of where scattering is strongest. They are also time-dependent. As time passes, the apparent ring radius changes. This creates a moving pattern in a static dust field. A limit of observation enters softly. The environment can confuse cause and effect. A shell can come from many sources. A halo can be produced by many kinds of outbursts. Without precise timing and without full three-dimensional mapping, association can be uncertain. This is a limit of attribution. Dust scattering can also distort the observed outburst profile. It adds delayed light that smooths fast changes. This is a limit on recovering the true burst shape from later observations. Another limit is distance. If the region is far away, faint shells and halos can fall below detection thresholds. Absence of evidence is then not evidence of absence. The limit of intuition follows. It is hard to imagine a short flash influencing a region a light-year wide. Yet a light-year wide bubble is not created by one flash. It is maintained by many events and by persistent emission over long time. Energy deposition integrated over years can drive a gentle pressure difference. That pressure difference shapes gas slowly. The analogy is quiet and unique. A shoreline can be shaped by countless small waves rather than a single storm. Each wave leaves a thin line of wet sand. Over time, the shoreline profile changes. In the magnetar environment, each burst is a small wave of radiation and particles. The shell is the changed shoreline in gas and dust. A fifth visual anchor settles on the bubble edge as it fades into darkness. The rim becomes patchy. Some segments are bright, others are nearly invisible. The surrounding mist drifts. The cavity remains as a subtle contrast. The next payoff is that environment can outlast activity. Even when the magnetar becomes quieter, the bubble can persist for a while. It fades as pressure equalizes and as gas refills. This adds another timescale. The star changes on thousands of years. The bubble can reflect that history over comparable spans. The section ends with a gentle transition. The surroundings have shown how magnetar energy leaks into the wider medium. The next section moves back to signals and what they can reveal, focusing on how timing and spectral changes can be used to infer magnetic geometry and stress without ever seeing the surface directly. A magnetar cannot be seen as a resolved globe, yet its hidden structure leaves a readable pattern in time. Pulse shape and spectrum act as indirect map of where stress and heat sit on the surface and in the near field. At this distance, the star is a steady point that blinks with a slow cadence. Each blink has a distinctive outline. One pulse rises smoothly and falls smoothly. Another pulse has a sharper crest and a deeper notch on the way down. The first small payoff is that geometry becomes visible through repetition. Repetition turns a distant signal into a rotating scan. A primary visual anchor forms as a rotating band of glow around mid-latitude. The band is brighter on one side and dimmer on the other. A narrow dark lane cuts across the band like a clean stripe. As the star turns, the bright part comes into view, then the dark stripe, then the dimmer part. The pulse profile mirrors this passage. A broad hump appears when the bright band faces outward. A shallow dip appears when the dark stripe dominates. A second payoff follows. Dip is not a missing energy source. It is a line of sight through a cooler or less emissive corridor. Pulse profile means brightness versus time over one rotation. The definition is brief. Pulse profile is the repeating light curve tied to rotation. The concept stays simple. Rotation carries different regions into view. Each region contributes its own mixture of energies. The mixed output creates a signature shape. A third payoff arrives in plain terms. Two different surface patterns can share the same average brightness. Their pulse shapes can still differ strongly. This is why time structure can be more informative than a single number. A number places the cadence. A typical magnetar rotation can be about 5 seconds. That is like the pause between two gentle ocean swells. The scale shift is quiet. A 5-second blink reflects a body only tens of kilometers wide. A fourth payoff follows. A slow spin makes the scan easier to separate from fast bursts. The signal has room to show its own baseline pattern. A second visual anchor forms above the surface band. A crown of loops rises and bends back toward the star. The crown is not uniform. Some strands are tight and close, some are wide and sparse. Between tight strands, a thin, luminous sheet appears. The sheet has a sharp inner boundary near the surface. It has a softer outer boundary where the glow thins into darkness. The next payoff is that magnetospheric structure can imprint on the spectrum. Spectrum here means how brightness spreads across energies. A brief definition fits. Spectrum is brightness as a function of photon energy. The plane picture returns. Hotter regions and stronger currents tend to produce harder emission. Cooler regions and weaker currents tend to produce softer emission. A fifth payoff arrives. If the crown becomes denser with plasma, scattering increases. Scattering can soften the emerging radiation. It can also blur sharp pulse features. Light behaves as if it passes through a thin fog of charges. A third visual anchor returns to the surface seam network. The seams form a web that is denser near the bright band. The web becomes sparser toward the darker lane. A narrow step along one seam casts a moving shadow line as the star rotates. The next payoff is that shadows matter even without a visible landscape. A tiny step signals a fault. A fault signals a preferred stress zone. A preferred stress zone can correlate with repeat activity. This is not a guarantee. It is a plausible link supported by patterns in timing and spectra. A limit of observation enters softly. Many different surface maps can produce similar pulse profiles when averaged over the visible hemisphere. This is a limit of uniqueness. A second limit follows. Magnetospheric scattering can mimic a change in surface temperature. A change in plasma density can soften the spectrum without any cooling of the crust. This is a limit of inference. The hidden cause cannot be singled out from a single measurement. Instead, consistency across many epochs is needed. Another limit is temporal. Bursts can temporarily reshape the near field. After a burst, the pulse profile can change for a while. That change can be interpreted as a new hot region or a new scattering layer. Both can fit. A sixth payoff arrives despite the limits. Even with degeneracy, some features are robust. Persistent phase-locked humps point to stable emitting zones. Sudden profile jumps point to sudden rearrangements. Gradual drifts point to slow evolution. A fourth visual anchor forms as a slow drift in the dark lane. Over many rotations, the lane seems to slide in phase. The dip in the pulse arrives a little earlier each cycle, then stabilizes. The next payoff is that phase drift suggests footpoint motion. Footpoint motion can come from crustal creep or from slow magnetic drift. The motion is small in distance. It is still visible in time because rotation turns distance into phase. The analogy is quiet and unique. A cloud bank can cast a moving shadow band across a mountain ridge. The ridge does not move. The shadow does because the cloud shifts. In the magnetar, the ridge is the rotating body. The shadow band is an emissivity corridor shaped by field and plasma. When currents redistribute, the corridor shifts. The pulse dip moves in phase. This matters because time becomes a ruler for invisible changes. A fifth visual anchor shifts outward into the surrounding dust veil. The dust halo shows a faint brightness gradient that fades with radius. Within the halo, a slight ring appears after an outburst. The ring is brighter on one side where dust is denser. The next payoff is that echoes can separate fast and slow components. The direct outburst arrives and fades quickly. The scattered echo arrives later and broadens the tail. This helps identify what belongs to the magnetosphere and what belongs to the path through space. A second number could be used here, yet caution keeps the section simple. The primary cadence already sets scale. The section stays with one main number. A limit of observation returns with a new face. Intervening gas can absorb certain energies more than others. That absorption reshapes the spectrum in a way that is not local to the star. This is a limit of spectral purity. The true emission must be inferred through uncertain foreground properties. A final payoff softens the uncertainty. Even imperfect maps are useful when they are consistent. A stable pulse template can act as a baseline. Deviations from that baseline mark real changes. Those changes can be tied to bursts, to afterglow, or to long-term drift. Over years, a slow trend in pulse shape and spectrum can indicate gradual relaxation of twist. Over short times, sudden shifts can indicate starquakes and reconnection. The section ends with a gentle transition. The signal has shown how hidden geometry becomes legible through time. The next section widens from signals to meaning, tracing how these patterns fit into the life cycle of magnetars across long cosmic intervals. A magnetar is a short-lived phase in a long stellar story, yet the phase reshapes its own future through repeated releases. The life cycle is a balance between stored magnetic energy and the gradual ways that energy leaks away. At this distance, the object is steady again. Its pulse is calmer. Its spectrum is softer. The surrounding cavity is faint. The first small payoff is that activity is not a permanent personality. It is a stage with a beginning, a middle, and a fade. The beginning follows formation with a strong internal field and a hot interior. The middle is a period of frequent stress adjustments and bursts. The fade is a period where the reservoir declines and thresholds are crossed less often. A primary visual anchor forms as a slow fade of surface patterns over time. The bright mid-latitude band that once dominated becomes narrower. Its edges blur into a gentle gradient. The dark lane that once cut sharply across the band becomes shallower. The surface looks more uniform, yet faint seams remain as thin arcs. The next payoff is that uniformity can be deceptive. A quieter surface does not mean a field has vanished. It can mean that the field has shifted deeper, or that twist has relaxed. A key concept is reservoir. Reservoir means the stored magnetic energy that can be converted into heat and radiation. The definition stays short. Reservoir is stored energy available for future release. The plain picture follows. A reservoir can be large at first and then slowly drained. It can drain through many small channels rather than one big spill. In a magnetar, channels include gradual drift, persistent emission, and episodic bursts. That matters because the burst rate is a measure of stress crossing thresholds, not a direct measure of total remaining energy. A second visual anchor shifts to the magnetosphere. The loop crown is still present, but it is less crowded. The luminous sheet between strands is thinner. Dark lanes are wider. The edge of the near-field glow is less scalloped and more smooth. The next payoff is that a simpler magnetosphere changes how bursts look when they do happen. With fewer trapped charges scattering as weaker, emission can escape with less reshaping. Pulse profiles can become cleaner. The spectrum can become less variable. This does not require any new mechanism. It follows from the same physics with different parameters. A primary number places the life stage. The active magnetar phase can last about 10,000 years. That is like a long stretch of recorded human history, yet it is brief compared with the age of the galaxy. The scale shift is calm. A phase that seems long from one perspective is a blink from a wider one. Within that blink, many fast events occur. Many slow drifts occur. The distribution of events is uneven. Some periods are stormy, others are quiet. A third visual anchor widens to the surrounding medium. The 1 light-year cavity is still visible as a faint shell. Its rim is patchy. One segment is brighter where it presses against denser gas. Another segment is nearly invisible. The next payoff is that environmental scars can outlast the strongest activity. The shell remains as a low-contrast boundary even as the star's emission softens. This allows the past to be read in space as well as in time. The shell slowly relaxes. Gas seeps back in. Dust drifts. The cavity becomes less distinct. The effect is gradual and gentle. A second core concept enters. Threshold-driven stress release means slow loading and fast release. The definition remains short. Threshold-driven means a system changes suddenly after slow build-up. The plain picture follows. A hillside can hold snow quietly. The snow layer thickens slowly. Then a small trigger releases a slide. Afterward, the slope is calmer and begins to load again. In a magnetar, the hillside is the stressed crust and magnetosphere. The snow is stored stress. The slide is a burst or flare. That matters because it explains clustering and quiet spells. It also explains why the object can appear stable for long intervals, then change suddenly. The analogy stays gentle. It does not require drama. It simply shows how thresholds work. A fourth visual anchor returns to the crust cutaway. The outer lattice looks slightly cooler. The deeper layers are still warm. The temperature gradient is smoother. Interfaces remain. The next payoff is that cooling changes mechanical response. Cooler crust can be more brittle, yet with less twist and less stress it can also be less likely to crack. The balance is subtle. Cooling alone does not guarantee more flares. Stress supply and magnetic drift decide the outcome. A limit of observation enters softly. No full life cycle is observed directly. Ages are inferred from spin down and environment. Those inferences depend on uncertain initial conditions. This is a limit of historical reconstruction. Another limit is population. Only a small sample is known well enough to compare trends. Selection effects exist. Brighter objects are easier to study. Quiet ones can be missed. This is a limit of completeness. The limit of intuition follows. It is difficult to imagine 10,000 years of gradual drift when the most memorable events last seconds, yet the slow processes are the background that makes the fast events possible. Without slow drift thresholds would not be reached. Without cooling emission patterns would not evolve. Without gradual relaxation activity would not fade. The next payoff is that the magnetar phase is a conversation between interior and exterior. The interior supplies field evolution and heat. The exterior responds with emission and occasional reconnection. Over time, the conversation quiets. The same structure remains, but it speaks more softly. A fifth visual anchor settles on the pulse shape late in the phase. The main hump is still present, the notch is shallower, the timing is steady. The spectrum changes slowly rather than abruptly. The next payoff is that stability can be a diagnostic. It suggests fewer large rearrangements. It suggests a magnetosphere closer to equilibrium. It suggests stress below threshold most of the time. The section ends with a gentle transition. The life cycle view has placed outbursts into a longer arc. The next section shifts toward a calm resolution, gathering the key physical threads and easing toward a stable perspective that holds extremes without urgency. A magnetar is an extreme object, yet the clearest understanding comes from holding its extremes in a calm frame. The same rules that shape ordinary matter still apply, only push towards sharper gradients and tighter thresholds. At this distance, the star is again a quiet point. Its pulse is steady. Its environment is faint. The first small payoff is that the magnetar is not defined by explosions. It is defined by structure. Strong fields, rigid layers, and a surrounding plasma respond to slow change and occasional release. A primary visual anchor forms as a close view of the surface under low light. The surface is not smooth. It has a mosaic of plates with shallow boundaries. Some boundaries are gentle ridges. Others are narrow troughs. Along one curved boundary, the crust steps down by a tiny height. That step casts a thin shadow line that moves with rotation. The physical detail is clear. A sharp edge creates a shadow. A shadow creates a signal. The next payoff is that a shadow line hints at stress history. Where a step exists, motion has occurred in the past. Where motion has occurred, future motion is more likely. The star does not need to be seen directly for this to matter. Rotational modulation can carry the imprint outward. A second visual anchor forms above that boundary. The near field is arranged into a fan of loops. The loops are close together near the surface. They spread with altitude. Between them, a faint glow fills a wedge-shaped region. The wedge has a crisp inner edge and a softer outer fade. The next payoff is that sharpness is often a boundary effect. Gradients matter more than absolute values. A steep gradient concentrates stress. A steep gradient concentrates current. Where gradients are steep, thresholds are reached sooner. A core concept enters with a brief definition. Gradient is a change in value across distance. The plane picture follows. A gentle slope spreads weight. A sharp step focuses weight at the edge. In a magnetar, edges and slopes appear in temperature and field geometry and in plasma density. That matters because many distinct phenomena are reduced to the same pattern. A steep change invites a sudden adjustment. A second core concept follows, also kept short. Threshold is the point where gradual change becomes sudden change. The plane picture returns. A bowed branch can hold tension quietly. A small extra load can cause a snap. The snap is fast. The loading is slow. The next payoff is that the magnetar's most dramatic moments are simply the snap portion of a much longer curve. Another payoff arrives. The long curve can be studied by watching what changes after a snap. After a burst, the pulse shape can shift. The spectrum can soften or harden. Those changes reveal which gradients were altered. A number places the field scale without heavy notation. The magnetic field can reach about 1 quadrillion gauss. That is like comparing a gentle breeze to a hurricane that is stronger by an unimaginably large factor, yet still expressed as the same kind of physical influence. The everyday comparison stays simple. A refrigerator magnet is small. This field is beyond ordinary intuition by vast margins. The scale shift is calm. Such a field is anchored in a star only tens of kilometers across. The influence extends into a region that can reach many thousands of kilometers. Yet the most important action happens in a thin outer layer. Microscopic lattice forces decide where a crust plate yields. A second number is avoided to keep the section centered. One primary number is enough. A third visual anchor forms as a slow-traveling brightness wave on the surface. The wave is not a moving fluid, it is a thermal front. It brightens one region, then fades. The boundary of the bright region is curved and slightly jagged. The jaggedness follows the seam network. The next payoff is that heat flow respects structure. Heat follows paths of easier conduction. It avoids barriers. It collects along certain corridors. This can create hotspots that persist for long intervals. Those hotspots can be the visible ends of deeper currents. A limit of observation enters softly. The interior field distribution cannot be measured directly. Surface emission is a filtered view. Magnetospheric scattering changes what escapes. Foreground absorption changes what arrives. This is a limit of transparency. Another limit is timing. Burst triggers cannot be predicted from first principles with current knowledge. The thresholds depend on microscopic defects and on slow drift rates. Those parameters are uncertain. This is a limit of predictability. A limit of intuition follows. It is difficult to imagine how a solid crust can crack in a place where gravity is so strong and the material is so dense. Yet a crack is not a hole opening wide. It can be a narrow shear along a fault-like boundary. It can be a millimeter scale slip distributed across a large area. In that region, a small slip can still reorganize currents. That reorganization can drive a large radiative response. The next payoff is that small motions can unlock large outputs when energy is stored in fields. The analogy is quiet and unique. A tightly wound spring can store effort silently. A small latch release can let it unwind quickly. In the magnetar, the spring is the twisted magnetic structure. The latch is the local failure of crust support. The unwind is a rapid change in currents and emission. That matters because it connects the microscopic to the cosmic without needing drama. It shows how a tiny release can open a pathway for stored energy. A fourth visual anchor returns to the environment. The faint shell at about 1 light year is still present, but it is softer now. Its rim looks like a watercolor edge. The brightest segment is thinner. The dim segments merge into background. The next payoff is that even the farthest traces fade. The environment relaxes, the star relaxes. The activity pattern changes from frequent sharp events to rarer gentle adjustments. The section holds the arc without rushing. Strong fields create gradients. Gradients create thresholds. Thresholds create intermittent release. Slow processes rebuild and reshape those gradients. This cycle continues until the reservoir diminishes. The section ends with a gentle transition. The key pieces have been gathered into a stable picture. The next section settles the story into a quiet, final perspective, easing from mechanism into a calm sense of scale and continuity. A magnetar ends the way many quiet systems end. Not with a final display, but with a steady return to balance. The calm answer is simple. A strong magnetic field stores stress, then slowly relaxes through heat and light. At this distance, the star is a dim ember. It turns in silence. Its pulses remain, but their edges soften. The first small payoff is that the most extreme magnetism still follows ordinary bookkeeping. Energy does not vanish. It changes form. It spreads. It thins. A primary visual anchor forms as a long patient view of the star against a dark cloud. A faint halo surrounds it. The halo is not sharp, it has a soft outer fade. The inner region is slightly brighter. The brightness is uneven across the surface. A pale band arcs around one hemisphere. A darker lane crosses it like a seam. The seam has a crisp edge on one side. The other side fades through a gentle gradient. The next payoff is that the shape of a gradient matters more than the overall glow. Where the changes steep currents concentrate, where currents concentrate, heating follows. Only a few core ideas are needed to hold the ending. One is equilibrium. Equilibrium means forces and flows balance over time. In plain language, equilibrium is a surface that stops changing quickly. A pond becomes smooth after ripples fade. A sky clears after a brief squall. That matters because a magnetar trends toward the same kind of smoothness. The star does not become empty, it becomes less uneven. A second idea is diffusion. Diffusion means a slow spread from crowded places to open places. Diffusion can be pictured as warmth creeping from a hot patch into cooler crust. It can also be pictured as twist drifting from a tight bundle into a wider magnetosphere. That matters because diffusion is silent work. It is the quiet path that lowers thresholds. It reduces the need for sudden release. A new visual anchor arrives inside the crust. The outer solid layer is about 1 kilometer thick. That is like the height of a steep mountain ridge. Within that thickness, stress is not uniform. Some layers are stiffer, some are more yielding. Boundaries act like seams in rock. A thin fault line curves for many kilometers around the star. Along that line, the surface step is small. Its shadow is thin, yet the shadow repeats with each rotation. The next payoff is that a small geometric step can carry a stable signature across great distance. A signal would not need detail, it only needs repetition. From there, the view lifts into the magnetosphere. The loop crown is still present. The loops are less crowded now, their spacing is wider. The brightest strands no longer braid tightly, they separate like ribbons that have lost tension. Between them, the glow is more transparent. The next payoff is that transparency changes what escape looks like. When fewer charges linger, scattering weakens. Light behaves as a cleaner beam. Variability becomes gentler. A limit of observation sits under this calm picture. The interior field cannot be seen directly. The crust is opaque. The core is deeper still. Only indirect clues exist. A signal would carry surface heat. A pulse would carry geometry. A spectrum would carry the imprint of scattering. Those clues are incomplete. Different interior maps can produce similar surface patterns. This is a limit of uniqueness in inference. Another limit is time coverage. Quiet decades leave many traces, rare giant events leave fewer. This is a limit of sampling. The next payoff is that uncertainty does not erase structure. It narrows what can be claimed. It still allows a stable arc. A stronger field relaxes. A weaker field relaxes more slowly. A third visual anchor forms in the surrounding medium. The old cavity around the star remains, but its rim is faint. The boundary is patchy. Gas seeps inward along the weakest points. Dust drifts across the shell. The rim loses contrast and becomes a broad haze. The next payoff is that space keeps memory, but memory fades. A boundary can persist longer than a flare. It can also dissolve without any sudden moment. Now the scale shifts outward and forward in time. The magnetophase is short compared with the life of the galaxy. Yet it leaves an imprint that can outlast the phase itself. An object would carry its spin. It would carry a cooling crust. It would carry a field that is still strong but less twisted. Activity becomes sparse. Bursts become rarer. The baseline glow becomes the main story. Another visual anchor returns to the surface map. The pale band is still there, but it is narrower. Its edge is softer. The darker lane is shallow. The seam network remains as faint arcs. The arcs curve smoothly. They meet at gentle angles. The whole pattern looks less jagged. The next payoff is that late-time behavior is still informative. A smoother map suggests that gradients have eased. Eased gradients mean fewer thresholds are crossed. The primary analogy settles into the final cadence. After a single raindrop falls on a still pond, rings expand. The rings thin. Their height drops. The pond becomes smooth again. The raindrop is not a flare. The rings are not waves in space. The analogy only carries one idea. Disturbance spreads and fades when restoring forces are steady. That matters because the ending of a magnetar is not a disappearance. It is a levelling. It is a return towards simpler patterns. A final limit of intuition appears softly. A field as strong as a magnetar's is hard to imagine as something that relaxes. Strength suggests permanence. Yet relaxation is not a weakness. It is a pathway. It is the route by which stored energy turns into heat and light without breaking the system each time. The last payoff is that extremes can be held without tension. A magnetar holds an intense field. It also holds a quiet tendency toward balance. At this distance, the star remains a point. Its pulse is a gentle rhythm. The halo is faint. The shell is softer still. The story settles into a simple frame. Gradients build. Thresholds release. Diffusion smooths. Equilibrium slowly returns. Nothing needs to hurry. The light continues to travel outward through dark space. The pattern becomes calm enough to let the mind rest.